Hello, I would like to welcome you to lecture 8 of 2FH3. We'll start this lecture talking about superposition principle as applied to continuous distribution of charges. In the previous lecture, we talked about discrete distribution of charges. We have seen how we apply the expression for the electric field. If you have a number of discrete charges at a number of points, we apply superposition. We determine the vector pointing from every charge to the observation point, and then we do a vectorial sum. In this lecture, I will show how we can extend that to continuous line charges, continuous surface charges, and the continuous volume charges. We cover chapter 4, pages 115 to 126 of the textbook. We have seen so far only one type of charges, which is the discrete charge, where the charge size really is in a volume that's too small, and we consider it simply to be one point where the whole charge is concentrated. The second type of charge that we'll consider today is the concept of a line charge, when charges align themselves in the form of a line, and in that case we talk about the linear charge density. So we have now an expression which is how many charges are there per meter. How much charge is there per meter. So we say we have 5 nanocolumns per meter. So this will tell us how dense is this distribution over this length. The second type of charge we're going to be seeing is the surface charge. This equivalent exactly when you have a sheet of paper and there is some dust on it. This dust may represent these charges, and the density of the charges can vary from one point to another in your sheet. And here, of course, we talk about the surface charge density. So it's a surface charge density. It's in coulomb per meter squared. So this is telling us in a unit area how much is the charge over there. The last type of volumetric charge we'll be discussing in this lecture is the volume charge density. When you have charge in the form of a cloud of charges filling certain volume. And in that case, we talk about the volumetric charge density as shown here, and the unit in this case is coulomb per meter cubed. Each type of one of these problems require its own way of solution, as we'll see in a number of examples. I will start by showing you a typical example it's very classical in electromagnetics, which determines the field of a line charge of finite length. So we have here this line charge here. It's extending between a certain length to another length, say along the z-axis. This is my observation point. I would like to calculate the field at this point B. This point B has coordinates rho, phi, and 0. So here rho means the distance between B and the wire. So this is the z-axis. This is rho, and phi, it is the angle of this point. Maybe if you try to draw a top view here of the wire. So if this is the wire, this is my observation point. So this is the line connecting them, and this angle here, if this is the x-axis, this will be your phi. So I'm now doing a top view if I look from this side, if someone looks from this side. So the result here, because of symmetry, because the wire here is in the middle, the result will not really depend on the angle phi. It will be independent of phi. A number of things to notice in this example, or in this figure. We have charges lining them up in a linear way. So we have a linear charge density. We call it rho L. And rho here does not stand for distance. It is simply, it's a classical way of writing a linear charge density. You write it as rho L. What we do, we divide this linear charge or linear distribution into small segments. Each one of them has length dz dash. And if this length is small enough, we consider it to be like a point charge. This is what we're really doing. We try to divide this wire into tiny segments, and every segment will have a charge of rho L dz dash. Now, what is the reason for this dash? I explained earlier in the lecture that it's a classical thing or a traditional thing in electromagnetics to call the coordinates of the source as a dash. Give them a dash in the coordinates. So this is here. This is the z dash direction. While my observation point, we give it coordinates without a dash to indicate that this is where we are measuring the field. A number of very important expressions we need to notice here. R is the distance between any arbitrary element on this wire and my observation point. Z dash is the height of this arbitrary element from the XY plane. And alpha is the angle between the direction of the wire as shown here and the direction of the line connecting the element to the observation point. Alpha varies between two values, alpha 1 in the bottom of the wire. So you can see when you connect this element here to the observation point, the angle that you make with the direction of the wire is called alpha 1. Alpha 2, which is this one here, and you can see this again, the angle between the direction of the wire and the vector connecting the differential element to my observation point. Of course, one other thing to notice, if this wire goes to infinity, so if this end goes to minus infinity down there, alpha 1 becomes 180 degrees, and if this end goes to the other side, alpha 2 becomes 0. So it's very important to remember these limits because we'll be using them later in our calculations. A number of very important relationships to notice here. The true distance here is nothing but r equal to r sine phi. Okay, so this is sine alpha, sorry. So rho is equal to r sine alpha. And this distance z dash is equal to r cosine alpha. If we replace r as I show here by rho over sine alpha, you can get that z dash is equal to rho cosine alpha over sine alpha, which is rho multiplied by cotangent of alpha. And this we will use it later in our calculations because we will convert all the integration in terms of alpha. So from this expression, if we differentiate both sides, we can see that if z changed by z dash, then alpha will change by minus rho over sine squared alpha d alpha. So we'll use this later in our integration. Notice that rho is a constant because we picked already one observation point and want to calculate the field at this point. Now it's very important to keep all these details in mind to understand all the vector and the mathematical manipulations that will follow. The coordinate of this point here, this point has only a rho, so it's only in the rho direction, while the coordinate of an arbitrary element along this wire, like this element here, is z dash in the direction of az dash. If we only consider one of these tiny elements on the wire, this is the electric field resulting from this tiny element at the observation point. So rho L dz dash is dq, is the charge on that point, which we really consider it like a point charge, divided by 4 by epsilon, and epsilon is the permittivity of the medium, multiplied by r minus r dash. R minus r dash is the vector pointing from that element on the wire to my observation point. So if I'm observing the field at this point here, this one here is r minus r dash. R dash is the position vector of the point of the element on the wire, and the r is the position vector of the observation point here. And of course, as we know from Coulomb's law, if you put the complete vector on in the numerator, you put the modulus cubed in the denominator. We know that, as I explained earlier to you, that any element on the wire which we consider it like a point charge has coordinates z dash in the direction of z. You can call it z or you call it z dash, it does not really matter because z does not change. It's one constant direction, and it does not have any coordinate rho because on the wire this is z axis, so rho is equal to 0 on the z axis. While for the observation point we agreed that its coordinate is rho a rho, and it's in the xy plane. We assume it's located in the xy plane. Z is equal to 0. Phi can be any value. Phi can be any value because if you take the top view here, this is one point. You can get another point there, a third point there, and so on. So phi is changing, which because the result should not change on phi. Does not bend on phi because there is some symmetry. If this is your wire in the middle, if this is your wire as I'm showing here, then the result should be the same for any phi as long as you are keeping the distance the same. So this is why we will consider only the case where phi is equal to 0. So now we'll start our calculation. We say, okay, we have, this is our expression. This is r minus r dash. We subtracted these two position vectors here, r minus r dash. will give you rho A rho coming from the observation point, and Z dash AZ coming from the from that point charge, which is really an infinitesimal element on the wire. This is the one here, okay? And then we know that the component coming, or the field component coming from that element will have two components. One is coming in the one B contribution will be in the rho direction, another contribution Z direction. This is coming from the fact that this vector has two components. What I did here, I substituted this term into this expression, and I replaced the modulus R minus R dash by this vector R cubed. So now what we'll have to do, we have to integrate over the wire, over the whole length of the wire, sum all the contribution the rho direction, sum all the contribution the Z direction to get the complete expression for the electric field. Notice when we integrate along the length of the wire to some contributions of different elements, AZ does not change, AZ is a constant, and the A rho is a constant. Why is A rho is a constant? Because I explained earlier, I fixed phi. So I'm talking about a specific phi. But A rho changes with phi. A rho is not a constant. A rho is actually, it depends according to cosine phi and sine phi, as we explained earlier. But because I'm fixing a certain phi, I can take A rho out of the integral as I did here, and I can take AZ out of the integral. AZ does not change. So here, what I did, I wrote the expression. I'm trying to sum the contribution coming from all points of the wire, from Z dash equal to Z min to Z equal to Z max. I'm doing it the same here. Now, what we did next, I used all these identities I explained to you earlier, that R is equal to rho over sine alpha, dz dash is equal to minus rho multiplied by sec squared alpha, so it's minus rho over sine squared alpha multiplied by d alpha. And then I convert the integral from z minimum to z maximum to alpha to be between alpha 1 to alpha 2. I would recommend that you do this yourself. Express z dash from the two previous slides, express r, and you will see many terms will cancel out, and you will have only 1 over rho coming out from these expressions here. This one here will have only minus sine phi left. This one here, because you have z dash, and z dash is equal to rho cosine r, so to r cosine alpha, sorry, to r cosine alpha, and you replace r by rho over sine alpha, you end up with a cosine here after you cancel a number of terms. Now, what remains is very simple. The integral of minus sine alpha is cosine alpha, both upper limit minus lower limit. The integral of cosine alpha is sine alpha, both upper limit minus lower limit, and this will give you the final expression for the field. So here we can see that the field resulting from this infinite wire, or not, actually it's not an infinite wire right now, it's still a finite length wire, so it's a wire like this at any point here, will depend on the distance through normal distance from the wire to my observation point B. This is the normal distance, and will depend also on the angles alpha 1 and alpha 2. This is alpha 1 from the end of the wire to the point, and this is alpha 2 from the start of the wire to the point. So if you can calculate all these angles, we can get the right answer. Now the case that you should remember, it's very easy to remember, when the wire becomes infinite. So this point here will tend to infinity. So this point here will go down to minus infinity in the z direction, and this point here will go to infinity. In that case, alpha 1 becomes 180 degrees, alpha 2 becomes 0. So in that case, you get cosine of 0 minus 1. So this will give you another 2, and this will be the expression of the field resulting. There is no z component will cancel out because sine 0 and sine pi are equal to 0. So there is no z component. The field will be only in the rho component, and this actually makes sense because the field resulting from some points will be in this direction. Field resulting from a similar point would be in this direction. They cancel each other out, and all this z component and only the rho component will remain. So z components will cancel, rho components will remain. This is very similar to some of the results we have shown earlier. So this is the expression. You should remember always this expression, that the field resulting from an infinite linear charge is inversely proportional to the normal distance from that wire, and it's pointing in the direction normal to that wire. Now let's take a look example at this result. We have here an infinite length of charged line. It has linear charge density 4 nanocoulomb per meter. It exists. It's a line, so it can extend anywhere in space. It's actually the intersection of two planes, x equal to 2 and z equal to 4. We would like to find the resulting electric field at the origin. So here the result is required at the origin. So I wrote for you the expression here for the field in general. It is equal to E equal to rho L over 2 pi epsilon naught rho A rho. Rho L is the linear charge density. We already know that. It's 4 nanocoulomb per meter. We know epsilon. Rho is the normal distance from the wire to my observation point, and the A rho is the direction of the normal distance from the wire to the observation point. So this is the direction that you will be using if the wire is really z-axis. Sometimes it is not the z-axis as shown here. So you have to be able first to define this unit vector, and you have to be able to define this normal distance. These two are very important to get the right answer here. As I urged you before several times, you have to start first by drawing a diagram. So here I draw a diagram of my problem. This is the charge here that we have. It's a line. It's parallel to the xy plane. It is the intersection of two planes, x equal to 2 here and z equal to 4 here. So it's really this line here. It's extending from minus infinity to infinity along the y-axis. This is my observation points at the origin. Then we have to determine the length rho from the normal distance between that wire to my observation point, which is the origin. And I have to determine as well this direction here, pointing from here to here, because the unit vector in this direction will give me A rho. If I draw a side view of this structure, so if what I do here, I simply say I'm going to be looking from the side here. So if you look from the side, what you will see that the y-axis becomes a point pointing out from the page. This is your line charge. It becomes like a point, and this is my observation point. So you could see here because we projected everything here on the xz plane, now you can tell what is the normal distance. Normal distance between them is this distance here, which is equal to square root of 4 squared plus 2 squared. And the unit vector pointing in from this point to the origin is equal to the coordinates of the origin minus the coordinate of this point, which has coordinates, of course, 0, x is equal to 2, 4 is, y is equal to 0, and z is equal to 4. So this direction here is actually rho A rho. We call it rho A rho because if I consider this to be the z-axis, I call this distance rho A rho. So this, you don't have to call it rho A rho, you simply call it r minus r dash. So r minus r dash is a vector pointing from my normal from my line of charges to my observation point. So it's equal to this point 0, 0, and 0 minus 2, 0, and 4. So this will give you this vector. But in the expression, I need a unit vector from here to here. So I divide by the length of this vector, which is equal to 4 squared plus 4. So it's give us square root of 20. So now we are all set to get the final answer. The expression of the field resulting from an infinite line charge is equal to rho L over 2 pi epsilon rho multiplied by A rho. This is rho L. This is a linear charge density 4 nanocoulomb per meter. 2 pi. This is epsilon, and unless I tell you otherwise, you take it as epsilon free space 1 over 36 pi to the minus 9. This is the normal distance between the wire and the observation point, the line charge and the observation point. And here, this is a unit vector we derived in the previous slide. So now things can simplify. Square root 20 by square root 20 will give you 20. 2 pi by 36 pi will give you 18. Go to the numerator, it becomes 72. 10 to the minus 9 will cancel 10 to the minus 9. So the answer that you will get here is 72 over 20 multiplied by this answer. And if you cancel 2 by 2, this is the final answer that you will get for the electric field. And of course, this answer makes quite sense. Because if you were to draw, this is the z-axis, this is the x-axis, this is where my charge was. So this one here this electric field which is pointing this direction has both a negative z and a negative x components as seen from these final numbers here. So this result indeed makes sense. We have here another example. We have a line charge. It's not really an infinite line charge here. It has length equal between it's extending on the y-axis between -3 meters to 3 meters. So it has a length of 6 meters only. It's not infinite. So we have to use the expression for the finite linear charge. And by the way, I don't ask you to memorize the details of the derivation. Just if you remember the final answer or write it on your cheat sheet. I know how to use it. We would like to determine the field at a point on the x-axis at 3, 0, and 0. So again, I start by drawing a very simple diagram to help me understand how the problem goes. So you can see here the charge is extending in the y-axis between -3 and 3, and this is my observation point. So I have to determine the normal distance between my charge and the wire, and this obviously is equal to 3 meters. I have to determine the direction pointing from this linear charge in the direction of my point, normal to the linear charge, and this obviously this is the x-axis. So you can also see that if you come from the side and try to draw a side diagram here from this point, and this what you'll end up seeing. You'll see the linear charge as a point. This will be z-axis, this is the y-axis, this is observation point. So this is here is the vector r minus r dash we have to calculate. And of course it's obvious, it is fully in the x direction. It's equal to 3ax. It's very simple here. And if I drew one more diagram just in the xy plane to determine the angles alpha 1 and the alpha 2 for my answer, this is the y-axis, this is the x-axis, this is my observation point. The linear charge extending between -3 and 3. So you can see and this distance here is 3. So you can see because this distance is equal to this distance, alpha 2 is equal to 45 degrees, alpha 1 is equal to 135 degrees. And of course, alpha 1 is measured with the vertical direction of the wire. So now we go back to the expression and substitute for these numbers to get the total field. And because of symmetry here, I can tell that I'm not going to be having any z direction. All z components will cancel. You are left only with 0 component in this as can be seen. Because every element here, say element here, will have another element on the other side where the z components will cancel out while the rho components add to one another. So here I make the final substitution. This is the expression I should be using. Linear charge density divided by 2 pi epsilon. Normal distance from the linear charge to the observation point. Cosine alpha 1 minus cosine alpha 2 in the A rho. And A rho is the normal direction pointing from the linear charge to the observation point. We know linear charge is 10 nanocoulomb. We know that. The distance between the wire and the observation point is 3, as we have seen. And we agreed that alpha 1 and alpha 2 and the alpha 1, one of them is 45, the other one is 135. This will give you 1 over square root 2. This will give you minus 1 over square root 2 with a negative sign. So you end up here with 2 over square root 2. So if you simplify things, 4 pi will cancel. 4 pi will cancel with 36 pi. And this will give us here 2 over square root 2. And if you simplify things, and I hope I don't make any mistake here, it's 60 over square root 2. And if you simplify that, you end up with 42.42 volt per meter. One word of warning, the expression I used here is slightly different from the one in the book, because the one in the book, they define the angle alpha from the observation point. So they say that this is, it's a little bit different. This is alpha 1. The way you define it, I think it adds an angle of pi over 2. It doesn't matter which one you use, whether the one I have here in my derivation, the one I have in my derivation is easier, or the one in the book. Just use one of them and know how to apply it. I am not asking you to memorize the derivation or anything. Just know how to use it and how to apply it. Both of them are fine. Both of them are equivalent because alpha 1 in one of them is equal to pi over 2 plus alpha 1 in the other one. So both of them are the same, but just stick to one expression and know how to drive it.